In this video, we will look at some background information that is required to understand the process of designing hardware using HLS. In particular, concepts related to processors, systems on chip, and how FPGAs enable the construction of custom hardware. First, some background material. We need to understand the environment within which we are going to be designing hardware, when it makes sense to design custom hardware, and how we identify and model the required functionality. First, we will be looking at the concept of an SoC or system on chip, since we will be using SoCs for the rest of our designs. This is not strictly necessary, and you could have something called a standalone digital design. But on the other hand, the SoC approach provides a lot of flexibility and options. And in any case, once you are familiar with this approach, you should be able to switch to pure standalone designs without too much difficulty. We will start by going over some terminology that is important to know in order to understand the design process. First things first, when we say a computer, what we actually mean is a CPU plus memory plus peripherals. We will go over this in a little bit more detail. Look very briefly at what it means to compile and execute a program. What is the concept of a system bus and why is it relevant to us? And finally, come to FPGAs. What do FPGAs enable us in terms of how we can build custom hardware? The overall organization of any computer, whether it's a top 500 supercomputer or the processor inside a microwave oven, is more or less the same. There is a CPU or a central processing unit that communicates with a large block of memory. In this case, you can see the memory layout, which is basically marked as addresses going from 0000 to FFFF. Hopefully you recognize that those are hexadecimal representations of numbers. The 0, of course, is the number 0 itself. FFFF is 2 power 16 minus 1 or 65,535. Generally speaking, when we are dealing with addresses in computers, hexadecimal notation makes it much easier to understand and use different ranges of values. So some familiarity with hexadecimal you will probably need to build. Again, in this case, the FFFF is basically because it's a 16-bit address that I'm assuming over here. If you had a 32-bit address bus, you would have up to 2 power 32 minus 1, which is roughly 4 billion locations. And if you had a 64-bit bus, you would have 2 power 64 minus 1 possible locations, which is basically much larger than any realistic memory that you can build. The memory communicates with the CPU using a data bus, which is bidirectional. You could either write from the CPU into memory or read from the memory back to the CPU. And finally, on the bottom left, you would notice that there is a block marked the bus, to which are connected the serial port, USB, A to D, etc. Those are collectively known as peripherals and essentially enable communication with the outside world. Nowadays, what we are talking about is that the most common configuration that you would see is something called a system on chip. This just means that a wide variety of peripherals and interfaces, they could be radio modems, cameras, touchscreens, have all been integrated onto the same silicon chip as is used for the processor core. Integrating in this way onto a single core makes it easier and in most cases faster for the peripherals to communicate with each other or with the main memory. And generally speaking, you get either more efficient or powerful designs. Either speed is better or the power consumption is improved, which is why people tend to go for systems on chip. In our case, we will not be looking so much at the system on chip from the point of view of particularly power consumption. Primarily, the goal is going to be how do we accelerate certain computations or get better speed by using hardware accelerators. All right, what about the internals of the CPU? Broadly, again, there is some very basic functionality that is required, and there could be a lot of other things that are added on. The sort of bare minimum that you can expect is an ALU, the arithmetic and logic unit, a bunch of registers, typically called a register file that is used to store temporary information, bus interfaces, the data in, data out, address out, instruction address, and so on, that are used to communicate with the outside world, a program counter that keeps track of where we are in the flow of control. That is, what is the address of the next instruction to read and execute. And finally, some control logic, which at its most basic form is just a finite state machine that takes inputs from the states of the various other parts of the CPU, looks at the present instruction, and decides what to do next. There are a bunch of state transitions that are defined, and the control logic basically executes those. Now, in practice, most processors will have many variations on this. Pipelining is used for higher performance. Shadow registers and switchable register files will be used for fast context switching. Various other modifications and improvements are generally designed into CPUs. However, these are not our concern, and we are not going to go any deeper into that at the moment. What we do need to understand is the concept of an instruction set architecture. This is basically the set of instructions that can be executed by a given processor. Typical instructions that you would be familiar with would include things like add, which basically could be used to add two registers and store the result in another register. Move, which could either take data from memory and bring it into a register, or take data from a register and move it into main memory. Jump, which changes the flow of control, allows you to jump to a new location in memory and execute instructions from there. Examples of instruction set architectures. The most common ones that you are likely to have heard of are probably the ARM architecture, the ARM ISA, and the Intel x86. There are less common ones, MIPS, the Power series from IBM, Microblaze from Xilinx, the Neos from Altera, and OpenRISC, which is an open processor design. Nowadays, the RISC-V architecture is rapidly picking up adoption, and in fact, lots of people seem to be considering that as the basis for SoC designs. So potentially that is something that could be useful in future. Now, what happens when you write and compile and execute a program? We will go over this using an example in a future video, but at the highest level, what happens is you start on the left-hand side, you write a program source code, let's call it hello.c. You use a compiler, and the compiler's first job is to convert that into so-called object code. It creates a file which usually has an extension .o in Unix-based systems. And this basically is a set of instruction codes which are in the instruction set of the target processor, right? The machine language instructions. Now, the hello.c by itself may have function calls like printf, which are not completely defined within your own source code, which means that these other functions need to be linked in from somewhere else. So there is another program called the linker, which is again typically called LD on Unix-based systems, which links and loads files to the object files together and creates something called an ELF, or an executable binary file. The ELF stands for extensible linker format. It is a particular type of binary format that is typically used on Linux-based systems and a lot of other microcontroller-based systems as well. These ELF files are meant to be executed on a target. If there is an operating system, it will take care of loading that file into a suitable portion of memory so that it doesn't interfere with other programs, and then jump to the beginning of the program and start executing instructions. The important thing that you need to understand over here is ELF files are not easily portable. What that means is that a file compiled for Linux will not directly run on Windows, because it assumes the existence of certain libraries and function calls that probably do not exist on the Windows system. And of course, vice versa. A program written on Windows will not run on Linux directly. For our purposes, the most important thing to keep in mind is we will be finally trying to run programs on another processor called the Microblaze. And in order to create the ELF files for the Microblaze, since we cannot compile directly on the Microblaze processor, we will be using something called a cross compiler that will run on your Linux system and generate ELF files that are meant to run on the Microblaze. All right, so all of this was regarding the software, which of course we will go over examples later. But for the time being, we need to understand something else, which is how does the processor communicate with the outside world? Typically, this is done by means of something called peripherals. Examples of peripherals that you would be familiar with include the serial port, sometimes called the UART or the UART, the disk, which is used for storage, keyboards, displays, mice, lots of other things of that sort. The processor communicates with each of these devices by means of something called the system bus. Now, at a very basic level, a bus is just a collection of related wires. What makes it useful is when specific modes of functionality are associated with the values on the wires. For example, if you have a flip-flop with a D input and a chip-enabled input, the combination of these two could be considered a bus. The idea being that when CE is equal to 1, D will be written into the flip-flop. So they are two related signals, and the combination of them specifies a functionality more than either one of them alone. Similarly, we could also have a set of wires forming an address bus. Another set forms a data bus, typically 32 or 64 wires that are grouped together and called a data bus. And maybe some other wires that indicate whether or not a read or write operation is required from the memory, whether the address is valid, whether the data to be returned is valid, and so on. The combination of these groups of wires together is sometimes called a system bus. So in the figure, you can see that on the left-hand side, there is a block marked microblaze, which is basically the processor. It has two wires that lead to something called the processor memory, right? The middle lower block. The DLMB and ILMB are used to communicate with the processor memory. LMB essentially stands for local memory bus, and the D and I stand for data and instruction. But apart from that, you will also notice that there is something marked the MAXI-DP. This is the master AXI data port, where AXI is essentially the advanced extensible interface, which is the bus that we will be considering for use with the microblaze processor. That the wire leading from that AXI data port essentially goes to something called the AXI arbiter or the AXI interconnect, and it goes to the S00_AXI interface of that, which means basically that that's a slave interface on that arbiter. The idea of masters and slaves will once again be explained a bit more in detail when we look at it with examples. But the important part over here is that AXI arbiter is the one that takes care of connecting between the microblaze processor and the peripherals. In our case, we have only a single peripheral, the UART, and the UART interface of the AXI bus has been expanded. So you can actually see that it has a large number of related wires over there. Going from the top, it essentially has something called AR address, which is basically some kind of a read address. There's an AR ready, which indicates whether the address is ready, AR valid, which is an input from the CPU indicating that the address is correct. Similarly, write addresses, write ready, write valid, a whole bunch of signals that you don't need to worry about for the time being, but which you will need to at least know that and be aware of how they are used in order to build a larger system. In future designs, we will actually be going through the process of building systems around these kind of buses. For the most part, you can just use them without having to understand the details of how the bus interface signals work, but having some basic understanding of that will help you to debug especially a lot more easily. Now, how does a processor actually communicate with the peripheral? We have seen that a system bus is used in order to connect the peripherals to the processor. And in addition to that, we use something called memory mapping, where a portion of the address space of the processor, that is, some of the addresses that the processor can potentially talk to, are used in order to map parts of the peripherals so that when the processor reads or writes from those addresses, it is indirectly talking to those peripherals. The figure shows an example memory map. This once again will become a bit more clear when we go through the example, but on the other hand, you should probably look at this and try and at least understand what a memory map looks like and how it could be used. The main thing that you need to understand over here is we have only one peripheral, the AXI UART. We have two blocks of memory, the slave memory interfaces on the LMB, the local memory bus, which basically correspond to the mem blocks that are indicated over there. You will see that they are divided up among the data and the instruction regions. But if you look at the addresses that are assigned to them, they are exactly the same addresses that are used both for the data and instruction. So in other words, this microblaze processor does not have a separate data memory and a separate instruction memory both overlap in terms of the address space. How much memory is available? That's basically 128 kilobytes. Where was that configured? That gets configured while we design the microblaze processor itself. And the address range into which that goes, that is the starting address and the offset address and the high address, are determined during the compilation, during the creation of the system. You can choose it, you can change those numbers if you want to. It is unlikely that you get much benefit by really hand coding them, so you are probably better off just letting the Vivado tools do the job for you. But if you need to, then you can control it. And of course, what you can see over here is that single UART has also got an address space associated with it. There is an offset address, the 44A00000, and a range of 64K addresses have been allotted to the UART, so that the high address basically becomes 44A0FFFF. Now 64K basically corresponds to 65,000 addresses, roughly 65,000 something addresses. Now, what do we use those addresses for? Effectively, what is going to happen is if I write to any one of those addresses, the arbiter or interconnect is going to activate or wake up the UART and say, look, the processor is trying to talk to you. You need to respond based on some part of the address that the arbiter will pass on to the UART. It won't pass on the entire 32-bit address. It will only pass on whatever is required for the UART. The UART will then decode that address and decide, is the processor asking for a status? Is it asking to send a new byte out on the port? Is it asking to retrieve a byte that has already been received on the port? And by interpreting the address and the read or write instruction appropriately, the UART can respond in any way that it likes. This means that the UART at one level is acting like a memory. The processor just needs to read or write a certain memory location in order to communicate with the UART. But rather than a sort of dumb memory block that only takes care of storing information and retrieving it, the UART can actually process it and return information that is enhanced in some way. This idea of memory mapping is something that is going to be very important in terms of actually building and using systems in future. So although you don't need to worry about how to allocate address spaces and so on, this becomes the core idea of memory mapping is going to be used in order to both map peripherals into your AXI address space as well as communicate with them using programs that are going to run on the microblaze. So now that we have a background on what a CPU is and why one would, or rather how you can write software that would run on a CPU, the next question that comes up is, okay, why would you ever want to use custom hardware? And this is actually a much more important question than it sounds at first. It is not at all a trivial question. If at all there is something that you can do with software, you should do it in software for the simple reason that software is typically much, much easier to debug and write in the first place than hardware is. The only reasons why you might consider writing custom hardware or creating custom hardware modules is because the software that you create is going to be constrained by the architecture of the CPU that you use. In particular, you might have two kinds of constraints. One is your software is not fast enough. You are not able to compute something quickly enough for your real-time requirements, or maybe it just takes too long. It takes many days to run when you want it done within hours or minutes. The other possibility is it consumes too much power. An example of this is when you talk about something that you want to run on an embedded system, perhaps a phone, let's say the latest neural network architecture that you want to get working on your phone, and you simply do not have the computational power that is available in Google's data centers inside your phone. So you want to make sure that it can be, you probably want to put in some kind of a custom hardware accelerator that will allow you to run this much faster and fast enough, but consuming far less power than would be required in a data center. So that has to be kept in mind. You do not just design hardware because you can. You should design it keeping in mind that it is much harder to design than software. Therefore, you should focus only on the parts that really require it. So how do we design hardware? this is where the FPGA comes in. An FPGA is something called a field programmable gate array. It's essentially, you can think of it as just an array, a two-dimensional grid of configurable logic blocks, where a logic block essentially has two parts. One is a lookup table, which you can think of as basically the truth table of a Boolean function and can implement any kind of combinational logic. The second part is a flip-flop or a D-type edge-triggered flip-flop. This is used to implement sequential logic that is used inside any kind of sequential hardware design. What this means when you combine it with something called a programmable interconnect is that in theory, at least, an FPGA can implement any kind of special or any kind of digital design. It is not restricted in any way. The only restriction will be the capacity of the FPGA and possibly the speed or any other constraints that you might get. The theoretical computational capability is essentially anything that can be designed using digital logic. Now, in addition to this, FPGAs nowadays typically also contain a lot of special purpose units. Why would this be required? For the simple reason that if you actually wanted to, let's say, multiply two numbers together, you have an option of creating a complete booth encoded multiplier, perhaps using just registers or flip-flops and combinational logic. However, this is not going to be particularly efficient. And if you know in advance that you are going to be doing a lot of multiplications, you might just want to have custom hardware units that are able to do multiplication very efficiently. This is precisely one of the things that is done inside FPGAs. They have something called DSP48 blocks. Those are hardware multipliers that can multiply 24 by 24 bit values. This, among other things, can actually be used in order to implement single precision floating point multiplications, but usually is used directly for integer type multiplications and can make it possible for an FPGA potentially to do even like something like 1,000 multiplications per clock cycle, which puts it completely in a different league from what a CPU could do. Block RAM is high density memory, much higher density than using a large number of flip-flops, however limited in capacity on the FPGA, typically only a few kilobytes to at most a few megabytes on the largest FPGAs. But it is very high density and can be used for storing a significant amount of information that cannot go into flip-flops, but at the same time can be accessed at very high speed through the FPGA fabric. There are also custom hardware modules such as clock managers, phase-locked loops, gigabit transceivers, and so on that can be used in certain circumstances. And some of you may in fact be using them for your designs. We will not look at them for our initial examples at least. There may be certain specific cases where we might need to use either a clock manager or a high-speed transceiver, but the main focus will not be on those. So putting it all together, we can now think of a complete system on chip that can be implemented on an FPGA. The control logic of the CPU can be implemented with the lookup tables and flip-flops, because after all, it's some kind of a state machine, while the block RAMs can be used for storage, either for the register files or more likely for caches or local memory. Now, in principle, almost any arbitrary digital peripheral can be attached to this SoC. Digital because certain things like A to D controllers or A to D converters, that is the analog portion of that, cannot really be implemented on an SoC because it doesn't have on an FPGA because it does not have the analog interfaces. But anything that is digital logic can in principle be implemented in the fabric of the FPGA. Now, this is the approach that we will use for the rest of this course. Why? Primarily because it makes certain steps such as getting data into and out of the system very easy, so that we can concentrate on the parts that need to be accelerated in order to get the highest possible performance and the behavior that we require from the system.